here, but also Blaine. In fact, I missed one opportunity working with Blaine when he was working on minimal tori, and I was doing really similar things, but he was quicker. So then we met in fact at IHES. He was spending a year there, and it took us 6 or 7 months to realize that we're each of us having one half of a theorem, which of course was no theorem. And when we started to discuss that, we had the theorem in what, 1 week or about that, which was a very interesting instance and the start of a very, very important relationship. So it's a great pleasure for me to be here. So my topic here is Dirac operators and submanifold theory. And I would like to, I will present some recent results, a number of recent results on this topic, but in a sense I would like to make it part of a plea for mathematicians to take spinors more seriously than they have been doing so far. So let me tell you something about spinors very quickly. Of course, the discovery of spinors goes back to Élie Cartan in his 1913 papers. He was classifying the irreducible representation and all of a sudden realized that there were more than what people believed. And so therefore he had to invent new objects, but it was more like an exception in the list. So his important book, La Théorie des spineurs, that he wrote in 1937, is of course one of the landmarks. It was translated into English only in 1966, so it shows already that the interest of mathematicians was kind of slow. The key term, of course, which made the spinors really very important objects in physics and absolutely unavoidable objects in physics, of course, is the work of Paul Adrien Maurice Dirac. At that time, he was interested in studying the wave function. He wanted to get Lorentz invariant equation for the motion of electrons, and that's the way he invented. He realized that the only way out was to renounce to the idea that the wave function of electrons would be functions, that they had to be spinor. So in a sense, this established the spinors as absolutely very fundamental objects in physics. And then there have been very few books on spinors among mathematicians. I want to stress this book by Claude Chevalet, The Algebraic Theory of Spinors, which has been recently republished. In fact, that's one of the books which I used a number of times, and basically every single library had the book stolen. And in fact, one day I was in Bonn, and I really wanted to have a book, and the book was not in the library, and I knew one person had it. It was Jacques Titz, and Jacques really basically let me use the book in his office and not in Anyway, so now there is a reprint of the book, and the book is more available. And of course, the work has been, the influence of Atiyah and Singer cannot be under stressed here, and the propaganda they made for mathematicians really take seriously the book. And in fact, one presentation of their work on the Atiyah-Singer and their theorem was very influential for me, and that's the first place I really studied spinors for good, which is this, the seminar notes by Richard Paley, a seminar which took place at the Institute for Advanced Study. That's 1965. And then really, for me, there's been a book that I've been using and using again all the time. I'm already using my second copy. The first one disappeared from my office at some point. That's the book by Blaine and Louise, Spin Geometry. And in fact, the whole purpose of my lecture is to try and convince you that it's really spin geometry exists. That is, one should really think a number of questions in geometry using spinors, which is something that physicists have been doing now for decades, but mathematicians have not yet really done that. And so the key question, of course, is that when one deals with spinors, in fact, as we know now in mathematics, it's very important when you study an object to study naturally defined differential operators acting on them. So you cannot speak of exterior forms if you don't have the exterior differential. You cannot speak too much about the spinors if you don't really use the two fundamental operators, which are Dirac operators and twistor operators. So I decided for this lecture to basically put twistor operators in the back. That's really more a matter of principle, because in fact they are hidden in many of the proofs that I will give, or I will not give. In fact, my belief is really, that's the point I want to stress, my belief that we are really on our way to really have a spin geometry, And today I would like to show illustrate this on one specific topic, which is submanifold theory. So this is what I would like to do. Of course, I will do a very quick glance at submanifold theory. It's so classical that it's almost shameful to show this slide, but maybe it's useful. At least it will just show some of the bias I would like to introduce in my lecture. So definitely the starting point of differential geometry was study of surfaces in 3 space, which is a typical instance where you study a submanifold in a larger space. And there are definitely 2 points of view. Either you look at a map, which you assume is, well, let's say, an immersion or even embedding from a manifold M into a manifold M bar, and then you have a given metric on the target space, G bar, and of course this immersion induces on M a metric, which I'm going to denote by G. And the whole game of submanifold theory is to study invariance of this submanifold with induced metric from the invariance you know of the larger manifolds. And typical case where this is done, and that's the whole game of submanifold theory, is that of course the ambient space is supposed to be special. That is Rn, Sn, Hn, anything you like, symmetric space. And in a sense you are studying submanifold lying in an isospace. And quite often you use the submanifolds to analyze larger space. And then you singled out, the whole theory, the whole point of the submanifold theory is to single out special submanifolds. So like being convex, being constant mean curvature, being minimal, being umbilical. So that's the first point of view, where definitely the object you want to put emphasis on is the submanifold itself, and not so much the ambient space, which is very well known. We know a lot about it. And there's, of course, a different point of view, which I'm not going to develop very much, but which I think could, I will give 2 examples of such a situation, which is a situation where really this manifold you study is a manifold with boundary. And therefore, you have a new manifold coming up, which is M underline, which is the boundary of M. And of course, M underline is a hypersurface in M. And the object you want to study is M itself, and not so much its boundary. Or sometimes you want to draw information from the boundary to the manifold. So it's a different game that you play in this second point of view. So let me start with one specific case, which is the case of hypersurfaces, which is known to be special in geometry, but in the case of spinors it will be also special. And of course, when you are studying the situation of a manifold M immersed or embedded in a larger manifold, dimension n+1, the basic invariant, of course, is the second fundamental form that you all know. But let me just say one word about it, because I will need this. In fact, very often the way the second fundamental form is presented in differential geometry is very technical. When I think the most efficient way is, again, a non-mathematical way, which is a mechanical point of view, which is you have the manifold M and you thicken it. So you think of it as some kind of a membrane, and you really want to study the membrane as a real object, which is, of course, not infinitesimally thin, but it has some width. And therefore, you have to get a parameterization of the nearby layers by so another manifold, which of course is very similar to M naught, which is this M that you are studying. And in this case, the second fundamental form is just, so of course you have the induced metric on M0, which is M, and also you have the induced metrics on the MS, which are the neighboring M. And then the second fundamental form is just the first derivative of the induced metric, up to a factor 1/2. And so, in a sense, in this point of view, to speak about second fundamental form, you really don't need anything about connections or anything. It's just a completely natural object in mechanical terms. From the point of view of a mathematician, maybe what you would say is that you want to study the larger space, the space in which you embed M bar, using adapted coordinates, and the adapted coordinates will be nonlinear coordinates on M, and then of course another parameter which you can take to be the distance to M. And therefore you have this very natural way of writing the metric on M bar in a nonlinear coordinate, which is basically the point of view I want to stress. Of course, another very important variant that you all know is the mean curvature, which is just a trace of H, the mean, so you divide by the dimension. So capital H is going to be the mean curvature for me, and I take it as a mean, really, that is, I divide by n. And it's very well known, it was already Bill just reminded us that it's the gradient of the volume functional. And in terms of connection, of course, it's very important to present the second fundamental form, and it's just a different, or two tangent vectors x and y. It's the difference between the, when you think of them as being vector fields on the larger manifold, the ambient one. So I call nabla bar, of course, the Levi-Civita connection of M bar, and then nabla, the Levi-Civita connection of G, the induced metric. And the second fundamental form is just a normal component of this difference. And of course, there is another point of view even, which is very important, which is so-called shape operator, which in this case, you view the second fundamental form as the variation along the submanifold of the normal vector. So you get this formula that h, xy tangent to m, of course, are just minus g bar, the covariant derivative of n, as a vector field in the larger manifold and in direction of x against y, and this is symmetric, which is not obvious. And of course, as is well known, there are two basic identities which really more or less shape the whole theory, the so-called Cadazi minority identity and the Gauss identity. And again, I want to stress that if you think in these terms, in terms of this point of view here of adapted coordinates, what you are just doing is computing some special components of the curvature tensor of the larger manifold, in this case with at least one normal component and three tangential components, and here with only tangential components. So in a sense, these identities are purely identities telling you, something special about computing the curvature tensor in adapted coordinates and relating this to the induced geometry on M. Okay, so in the general case, of course, you knew everything, all of that, but this allowed me to introduce my notation. So the general case, of course, is a case where you are embedding M in a larger manifold, but then the dimension is larger than 1. And I just want to stress again that the point of view of thickening is still very useful and very fruitful. And there's this absolutely beautiful article by Herman Weil on the volume of tubes, which contains a lot of deep geometry in it, characteristic classes and all of that. So of course, in this case, the function you get is a function of several variables, all the variables in the normal bundle. And in that case, the second fundamental form is a more complicated object. It's still a symmetric tensor field on M, the submanifold, but then you have to tensor it. It takes its values in the normal bundle. So it's a more sophisticated object. And then the mean curvature, of course, you take a trace on the tangential components, and therefore you end up having something which is just a section of the normal bundle. Therefore, very often one presents it as a mean curvature vector, and it's a normal vector field. And in fact, there is a main new ingredient, which has been, of course, when has to live with it, and in some sense, in geometric terms, I don't think really there has been a very deep geometric study of it. It has been taken as granted. Is the fact that the normal bundle, of course, inherits a natural connection, and there is no reason why this connection should be flat. So there is a connection there, and you have to do something with it. And I think one thing which I feel is not really satisfactory is to relate geometric properties of the submanifold to the connection on the normal bundle. I think a lot of things has been done very technically. I think probably some work still can be done in less technical terms, really putting more the emphasis on the geometry. And let me just finish this very quick and, of course, elementary presentation on submanifold theory by saying there is one intermediate case which is extremely interesting, which is the case of codimension 2, and typically for manifolds which are complex submanifolds of complex spaces, because that's the case of codimension 1 in the complex geometry. And of course, in that case, many things had to be thought differently. In particular, the normal bundle then is a complex line bundle. So you are back to one dimension, of course, one complex dimension. So this case mixes up many of the different things I've said. And in particular, one case which I feel is especially interesting and probably has not been completely exhausted is the study of hypersurfaces in the sense of these complex hypersurfaces, or more generally, two manifolds in the spaces of 4 dimensions, because you have some kind of a duality between the normal direction and the tangential direction. So let me come now to my story, which is really the study of spinors and Dirac operators. So I will start with hypersurfaces, because it's a simpler case. That's also the case in which we have more results. So I'm still working in, as I said, with an immersion or embedding of a manifold M into a larger manifold with which has dimension 1, n plus 1, when n is n-dimensional. I assume that m bar is spin, and then it's very simple to see that, of course, since m bar is spin, you have. I'm going to work with complex spinners, basically for convenience. In fact, for some of the things I'm going to say, it turns out to be interesting to go to the real spinners, but then it's kind of cumbersome to discuss. You have many different cases. Okay. Okay. So, yes, I'll try that. I skipped that. I thought. So you see that it shows my campaign is really necessary. That's another proof. No, I'm going to answer your question. Okay, so you see the difficulty there is the following one. So in fact, it's well known, very basic object. Maybe I will use the blackboard for 1 minute. The very basic object is the following one. So I'm really working with a vector space V and endowed with a Euclidean product G. And of course, it's well known that then you have well, I assume also the vector space is oriented. Then you have the group of orthogonal transformation which are determinant 1, that is preserving orientation of this SOVG. And this group is not simply connected, and therefore it's important to consider the universal cover, which is the sole group. So in the case, of course, where you take this to be Rn with a Euclidean metric, then you ended up having a group, it's spin n, which is the double cover of SON, which in this case I'm denoting the special orthogonal group by SON. So it turns out this group is not simply connected, but its fundamental group is just Z over 2Z. Therefore, just by taking a double cover, you end up having a universal cover. So in a sense, you have a basic fundamental exact sequence, which is this sequence. So this is for the theory of spinors, the absolutely fundamental sequence. So it means that from the geometric point of view, so in a sense, because I have this projection map here, so the key point is to realize, to give a very concrete construction of this group. And the best way of doing this is to work with the Clifford algebras. So Clifford algebra is just a quotient of the tensor algebra by the bilateral ideal generated by elements of the form x tensor x plus g of xx times 1. So in a sense, in this algebra, you force the relation that x, so on this quotient, because I took the quotient of this algebra of an ideal, I do have a new algebra, and they denote the product with a dot, that's the Clifford product. So I'm forcing the relation that the square of an element is minus xx. Minus the norm squared of the element times 1. So in this new algebra, which is the so-called Clifford algebra of the vector space G with respect to the scalar product G, the scalar vector space V with respect to the scalar product G, then you have this relation which is satisfied. And then you can prove that actually inside the multiplicative group of the Lie algebra, you can really very concretely realize this spin n. And this, of course, is very interesting because in that case, you have a very concrete representation of spin n as matrices acting on some vector space. So that's the starting point. And now when you want to do geometry, so I'm coming to my spin condition, how do the spin condition come up? Of course, when you do geometry, you don't stop here. So I have to go to the other side, destroying the beautiful pictures. So, in fact, you have the following situation. When you are working with a manifold M, it's very useful to work with a frame bundle of linear form, linear basis over the tangent space. And, of course, if you give yourself a scalar product, you have a very natural subbundle sitting there. And, of course, if you assume M is oriented, so you have a very natural subbundle here, which is just take the orthogonal, the bases here, which are orthogonal bases and which are direct. for which the determinant, which give you the right orientation. And of course, this was a GLN principal bundle. This one, of course, is an SON principal bundle. So now here comes the question. I would like to work not just with objects of this type, which corresponds to my group there. I would like to work with the objects which on which the group spin and operates. So in a sense, I would like to get pointwise a double cover of this bundle here. And it's just from this exact sequence you can easily see that you cannot always do that. So I would like to create a new bundle, P, which will project onto this, so that over each point I do have, so since these are principal bundles, above each point I have a copy of GLN. For this one, I have a copy of SON for this one. So for this one, I have a copy of spin n. So I want that this projection is so that when I look at above each point, I do have a double cover spin n over SON. And you cannot always do that, but you can, when you can do it, when you can actually find such a double cover, so you say that n is spin. And the topological condition to do that is, in fact, can be a certain characteristic class, which is the Stiefel-Whitney class W2, which belongs to m with coefficient in z over 2z. And the condition, this is equivalent to the vanishing of the second Stiefel-Whitney class. So you can do it for some manifolds, you cannot do it for some others. Typical examples where you cannot do it, you take CP2. CP2 is not spin. So what I'm saying, you cannot do it over CP2. But you can do something slightly different, which is called so-called spin C structure, which I should have done all my lecture with spin C structures, but okay. Is that okay? Or? Okay, so let me move on. And so typically, I'm sorry, one thing I should have said, then I spoke about the group, I didn't speak about its fundamental representation. It's well known that the fundamental representation of SON is just Rn, and here you have a fundamental representation whose dimension is depending when n is even or n is odd. That's where the theory simplifies if you are working with complex spinors, which I'm going to do. And then when n is even, of course, it means n is equal to m, and the space of spinors has dimension 2 to the m. When n is odd, you have two spaces of spinors, so of course n is 2m plus 1. And you have two copies of a space of spinors of dimension 2 to the m. And these two representations actually, as representation of the Clifford algebra, they are not equivalent, but as representation of the spin group, they are equivalent. So you choose the one you prefer. Okay, so let me move on. So you have this bundle of spinors sitting over this manifold, and it's a complex spinor bundle of the dimension I mentioned, depending on the dimension, the oddness or evenness of the dimension. And of course, when I say that I pick a spinorial metric, which means I choose such a spin principal bundle, and in fact there may be several, so then depending on the fact that the manifold is simply connected or not, or depending on its H1 with coefficients in z over 2z. So I choose such a metric. And of course, it turns out that the orientability of m, for this m embedded into m bar, I assume m bar to be spin, automatically it gives me that m is spin. So typically, and also not only this, but m inherits automatically a spinorial metric, which means that the choice of a spin structure on m bar and the choice of a normal, m being orientable, is the same as being transversally orientable. So it means I can select a well-defined unit vector field which is normal to m. So with this choice of a normal vector field, I have a natural, well-defined metric gamma on m, which is spinorial, which means I've chosen a spin structure and have a metric. And so in fact, the whole business is, has to do with the two bundles. A priori, along m, you can consider two different spinor bundles. Of course, m is a spin manifold itself with a spinorial metric, so you have the bundle of spinors over there. But there is another bundle which comes up naturally, which is along m. You can look at spinors for m bar for the spinorial metric gamma bar. And actually, so it's very important to compare those. And actually, you have the following phenomenon, which of course, if I was dealing with real spinors, the discussion would be more cumbersome. So I'm doing with complex spinors. If n is even, actually these two bundles are absolutely equivalent. And when n is odd, which means of course that n plus 1 is even, then actually you have you get for sigma bar the direct sum of two copies of the spinors along M. So in a sense, one thing which is very important, not only you do have this identification, but it's very important that you understand that the Clifford multiplication in one bundle and Clifford multiplication in the other bundle, they are not written exactly the same. In particular, Clifford multiplication here, when you translate it into here, you have to insert the normal vector as between the vectors. So it means Clifford multiplying by x here is like multiplying by x, then Clifford multiplying by the normal vector field, then applying this to the spinor field. So it's very important to have this. So as a result, the basic object, which has been considered by many people, but I think the two people who really discussed it, I'm sure it was present in physics before, but the two mathematicians discussed it are mathematician from the Czech Republic, Jan Bureš, and the Polish mathematician, like Trotman, who is also a very good physicist. And so they introduced what they call the hypersurface Dirac operator. So my spinor field psi here belongs to this bundle, which, as you know, is isomorphic to the other one. And the formula is exactly this one. So you get the mean curvature coming up as a function in front of the spinor field. And then you get minus n Clifford, then this computation. So psi is a spinor field lying in this bundle. So of course computing its covariant derivative in the direction of a tangent vector to m is meaningful. So this, of course, this formula is meaningful. So this is what we take. And of course, the key point is to study the properties of this operator D. So I made a selection of some properties which have been established recently. As usual, when one studies such operators, there are various questions which come up naturally. Of course, controlling the eigenvalues, getting upper bounds, getting lower bounds, and getting also some very specific equations that this operator satisfies and that you would like to discuss and relate them with the geometric properties. So I start with upper estimates. So as you know, because this one comment I want to make is that with this definition, D is a self-adjoint operator. In a paper I'm going to discuss later by Ed Witten used a Dirac operator on the submanifold, and the choice he made the operator not self-adjoint, which of course is not a sin, but then you have to be careful when you are working with it, that actually you don't do as if it is a self-adjoint operator. So now, I'm moving to the first theorem, which is getting upper estimates for the lowest eigenvalue of this hypersurface Dirac operator. In fact, the first work was done by Angel, 1993, and then the most precise result is due to Christian Baer, 1998. So here you have the following statement. So you take M, which is a compact orientable hypersurface immersed in Rn plus 1, and then you have the following estimate for the lowest eigenvalue. Well, I forgot to write the eigenvalue, so bad news. So it's 4 times lambda 1. 4 times lambda 1, the volume of mg is less than n squared, lambda 1 squared. It's less than n squared, the integral over m of the norm square, of the square of the mean curvature. So you see it's an interesting lower bound which relates the eigenvalue to the extrinsic geometry of M, which is an interesting thing. As usual, getting upper bounds for such self-adjoint operators is not very difficult because a priori, except when you get such a very nice geometric quantity, it's valuable. For the reason that you just apply the usual Rayleigh-Ritz definition of eigenvalues, and in order to get an upper bound like this, you just get the test function or test section of the bundle you are considering. So you get the test spinor field, and you just put it in the Rayleigh-Ritz quotient and just compute and get that. So the key idea, of course, use the fact that Rn plus 1 has a lot of parallel spinors. So you just take a parallel spinor, insert it in the Rayleigh-Ritz quotient, look at its restriction on M, and compute, and you just get that. So that's the idea. Of course, getting lower estimates is much harder because then you have to go deeper into the geometry. And I think the first lower estimate is due to Jazzy, Montiel, and Tsang, last year, 2001. So let me state the theorem. So you start with a manifold M, which is a compact submanifold of a spin manifold, M bar G bar, for which you assume that the scalar curvature is non-negative. In fact, they also have results when the scalar curvature is negative, but it's more cumbersome to state, so I just made a selection. So if the manifold M has a non-negative mean curvature and bounds a compact region omega, then twice the first eigenvalue of the hypersurface Dirac operator is larger than n, which is the dimension of the manifold, times the infimum of the mean curvature. So in that case, of course, you have to compare these two, and you get something interesting. And what's even more interesting is the fact that in case you have equality in this lower bound, which shows that you are really optimal, it means that so I said that this M is compact, but bounds a compact region. Then in that case, omega G bar, omega is an open set in M bar, omega G bar is actually a Ricci flat, and M has constant mean curvature, so H is not just a non-negative function, it's a constant. And actually, if you look at the eigenspace attached to lambda 1, which I denote by V lambda 1, it's exactly the space of parallel spinors on omega that you restrict to M. So in this case, the equality is characteristic of very nice situations where you control everything. So how do you prove such a theorem? Well, you make use of a formula which has been extremely useful in the whole use by mathematicians of Dirac operators, the so-called Lichtenowitz-Schrödinger identity, which is, very well known. So I stress again, which maybe is something which is not so well known. The formula was established by Lichtenowitz in 1963, just when he heard about the proof of the index theorem for Dirac operator. Singer told me that he knew how to do that at the same time, but in fact much earlier than that, in the late 30s, Schrödinger has done this computation and actually given this formula. So it should really be called the Schrödinger identity. But anyway, mathematicians tend to be chauvinistic. So here is the formula in the form that we are going to use it. So you have the hypersurface Dirac operator. You have so this is an identity for any psi, like any spinor field. And you integrate d psi against the psi. You subtract minus nh over 2 psi squared. So it's very much like the first term I gave for the hypersurface Dirac operator. So this is computed on M. And you remember M was bounding a space omega, a domain omega. So in omega you have something which is more the usual Lichtenowitz-Schrödinger. So in a sense, this is the boundary contribution of the Lichtenowitz-Schrödinger formula. And here you get the 1/4 R bar, which looks very much like this one. By the way, there should not be a bar here. So if you write this on N, there shouldn't be any bar here. Or you put bars everywhere, which maybe is better because that's what I'm doing here. So I'm going to put a bar everywhere. So I wrote the formula in M bar. And then you have this extra term, and here comes up the twistor operator. And that's the way you get an inequality, because actually this quantity is very nice because that's plus a norm squared, and the square is missing. And therefore you know the sign of this, and therefore you get, and when you get equality, then you are sure that this quantity is zero. And this is a very overdetermined equation, and therefore you get to the existence, the Ricci flat and everything. And there are really two nice consequences. One is a statement that all of you know, of course, the only compact embedded hypersurface in Rn plus 1 with constant mean curvature are round spheres. That's the Alexandra Theorem. And the interesting point is that here you get the spinor proof of the Alexandra Theorem without using any of the ideas of Alexandra before. And this was done again by the same authors, IHES, Montiel, and Sang, which I think is exactly one step in the direction I told you, namely one has to rethink a number of theorems in geometry in spinorial terms. But what is the interest? Well, you get other theorems which you couldn't get by the Alexandra method. And typically here's one. If you look at minimal compact hypersurfaces in spin manifold admitting a non-trivial parallel spinors, they're automatically totally geodesic. Which, of course, if you just apply the usual techniques of submanifold theory, you never get such a thing. And the reason is because the presence of a parallel spinor really is something which is so overdetermined that finally you end up proving such a theorem. So that's one family of results that I wanted to present in this direction. There are some others, but all these results have been obtained in the last 3 years, so it's kind of interesting. Another family of examples I would like to present is some kind of a revisiting of surface theory, which has been done by the Berlin School, by Ferus, Pinkel, Friedrich, in a long series of papers. They have revisited the very classical surface theory, showing that one can think of it in what they call quaternionic terms, which in fact this quaternionic approach is in fact a completely Spinorial approach. And so I just quote from them. There's a long series of papers. I just selected one, which I like very much, which is a theorem by Thomas Friedrich, 1998, which is the following one. So you take a two-manifold, so a surface, Riemannian surface, and you give yourself on this manifold a function, f. Then the following three data are equivalent. First data, you give yourself an immersion of the universal cover of M. So I should have also the twiddle on the universal, on the metric. So you get you lift the metric to the universal cover, and you get an isometric immersion with a mean curvature exactly the prescribed function f. So that's your first data. Second data, you have a solution of the Dirac equation, deep psi equals f psi. F is a function, so it's an almost eigenfunction, eigenspinor. But you insist on psi having norm 1. And the last thing is a pair, which is made of a psi and a t, consisting of a symmetric two-form, t, whose trace up to 1/2, that's again a mean curvature business, is f. So in a sense, t is a candidate second fundamental form, because f is the mean curvature, and a spinor psi satisfying this overdetermined system, where the covariant derivative in direction of x of psi is 1/2 t twiddle x, so t is a bilinear form, so twiddle means I transform it using the metric into a linear map, endomorphism. Apply to x, then Clifford multiplication with psi equals 0, so this is the star identity. So these three different data are actually completely equivalent. If you give yourself 1, you can construct 2. If you give yourself 2, you can construct 3. And if you have 3, you can construct 1. And in fact, just recently it has been extended by Bertrand Morel to the case of S3 and H3. And how do you connect this with the surface theory? Well, it's a very interesting thing. You see, as I said, the star equation is very overdetermined. When you look at the compatibility condition for this overdetermined equation, you ended up having exactly the Cadazi minority equation for t, and you get the Gauss equation for t. So in a sense, you have all the data to reconstruct a submanifold. So it's a typical case where, in this case of surface, you can actually do usual submanifold theory or do spinor theory. So that's something I like. One thing I want to mention is that in this theorem, one sees appearing an object which I like very much, which is this object, which also the physicists have been playing with for some time, because they call it the stress energy tensor attached to a spinor field. So I call cube psi the following quantity. It's a bilinear form, which evaluated over 2 tangent vectors is just the following thing. You take 1/2 of the real part of the Hermitian product between the covariant derivative of the spinor field x in the spinor field psi in direction of x, and the scalar product with the spinor field, which is psi multiplied by y. And of course, this is a priori has no reason of being symmetric or real, so you just have to symmetrize it. There's a plus missing here. Okay, so this is a bilinear form in psi. And so in a sense, in my previous slide, it's the t which showed up. And in fact, it's very interesting because this quantity here is exactly the gradient of the eigenvalue lambda in the space of metrics for an eigenspinor like this. So suppose you are interested in studying how the eigenvalue lambda varies when you vary the metric at a given eigenspinor. And then actually the quantity which appears, which measures how the lambda varies, what is the gradient of this functional lambda, you just get this Q. Therefore, in a sense, the vanishing of Q means that the eigenvalue is stable in a sense. So let me just give one example of two results, one result, but which is of course connected to another one, which has to do with the theory of submanifolds as boundaries. Remember, I told you there are 2 points of view. Either you're interested in submanifolds in themselves and in their intrinsic geometry, or you think of manifold with boundaries. So in fact, the person who really introduced that in the most beautiful way is Ed Witten in 1981. So he proposed his own approach to the positive mass conjecture. So it's in 2 minutes, I will say what is the positive mass conjecture. So it's a bit too quick, but I don't think I have no choice. So in fact, you are considering in general relativity a space-time which is a so-called isolated space-time. So mathematically, it means that you have something which is an asymptotically flat space-time. It means that the metric outside a compact region starts to decrease, and you can get a chart of the space-like slice of the space-time on which the metric decays in a certain way at infinity and decays to Minkowski space. So, in fact, it decays to Euclidean space. So, you need the decay to be very precise, not only in the metric, but also in its derivatives at the proper rate. And in that case, you see, one of the very surprising things when you study general relativity is that it's very difficult to get some kind of an estimate of what should be some kind of a local density of mass. There is no notion of density of mass in general relativity. But for these isolated systems, the good surprise is that you can introduce a mass as a limiting integral over large spheres in this space-like hypersurface. So when you compute this integral, which has to do with some derivatives of the metric, then you have a quantity. And so in physical terms, when the right-hand side of the Einstein equation, which is a stress energy tensor, has reasonable properties from the physical point of view, you would expect that the mass should be non-negative. But it was for a long time a conjecture that this was actually the case. It was verified in a number of very specific cases, but it took a long time before there was a general proof. So the first proof was given by Yao and Chain, but it was by minimal surface theory. But so Ed Witten proposed a different proof, which used he proved that m was positive because it was the integral of the norm squared of something, which is a good reason for a quantity for being non-negative. And what is this quantity? This quantity was a harmonic spinor, namely a spinor which is annihilated by the Dirac operator, that he found as a solution of a boundary value problem which has proper decay conditions at infinity. So he required that the spinor would decay at infinity like a parallel spinor and be asymptotic to a given parallel spinor on I told you there's an outside chart like R3, like the outside of the ball in R3, so you like the spinor field to look like some kind of parallel spinor in R3. I mean, the people were not so convinced about the analytic proof that he gave of the existence of the spinor field. So there has been another paper later, which was by Taubes and Parker, in which they gave more detail on the analysis, which is the underpinning of the existence of this harmonic spinor. But what I want to give you to show this boundary point of view is so application of this approach to the case of the outside of a black hole in a space-time. So again, you are working in a space-like slice of a space-time, and of course the induced metric is a Riemannian metric. And here is a theorem which was proved by Mark Herzlich in 1997, which you can state as a purely mathematical theorem, but the motivation was, of course, general relativity. So you give yourself a 3-manifold which is Riemannian, and you assume, so it's a non-compact one, you assume it's asymptotically flat in the sense I mentioned. That is, in an appropriate chart outside a compact set, you have a nice decay of the metric towards a Euclidean metric. And you assume that in this 3-manifold, you have embedded into it, you have a connected surface, which is the boundary of M, which is a 2-sphere, and assume that this 2-sphere lies minimally in this 3-manifold. And you also have to assume that the scalar curvature is non-negative. This non-negativity of the scalar curvature is very directly related to the assumption I made about the stress energy tensor. The stress energy tensor represents positive density of the physical fields, then automatically these induces are to be non-negative. Then you get the following estimates. You get that the mass is at least this quantity here, which is the square root of the area of the boundary divided by pi, multiplied by a certain quantity, which is like sigma, is like an isoperimetric constant, and which is computed completely on the boundary. So, I'm sorry, I put an m here, but it should not be an m, it should of course be, it should be, it should be the boundary of m, I'm sorry, there's a boundary missing here, so I don't miss it here. Okay? And so what is this quantity? So it's, as I said, an isoperimetric quantity here with a normalizing factor. What's interesting about this inequality is that it's optimal in the sense that if equality is achieved, then automatically mg is actually really the special. Oh, I'm sorry, I stopped right is achieved if this is the spatial metric. My apologies for this. Of the Spinorial metric with mass 1/4 of this. Apologies for this. So actually, so it shows that, I mean, this inequality is quite sharp. So how do you prove such a theorem? Well, again, you have to find a harmonic spinor, which is going to be the quantity by which you evaluate the mass as being the integral of something. And the way you solve it is by giving yourself some nice boundary conditions on the two sphere. And the nice boundary condition amounts to the following. That is, you are going to use the so-called T-Singer boundary condition. That is, you compute the induced hypersurface Dirac operator on these two spheres. And you are going to assume that the spinor field that you're looking for has only half, in a sense, look at its components on the eigenspinors there, and you require that it has no components on the eigenspinors with negative eigenvalues. So, in a sense, it's a quite global boundary condition on the two sphere, but which is the boundary. And thanks to this, you finally find this estimate. So, in fact, this was considered as one step in proving the so-called Penrose conjecture. Penrose conjecture was to say that you actually can bound the M exactly by this quantity here. And actually, this has been proved now by Biskin and Mannen by a completely different method. But this method here has some advantages over the other one. Actually, I stated this in 3 dimensions, but there's an n-dimensional version. When for the approach by Mannen and Biskin, there is no possibility of extending this to higher dimensions. Actually, it's just not true. The method fails dramatically. So this Penrose conjecture, which is interesting in terms of physics, says that the mass of a space in which there is a black hole, you should be able to control, get a lower bound of the mass by the area of the horizon of the area of the horizon of the black hole. Okay, so that was an example I wanted to give of a result thinking of the manifold with the boundary and using the boundary to get estimates on the Dirac operators. So now the last part of my lecture will be in the case of higher dimension, and there it's much harder. And let me explain what's happening there. So in this case, you really have full dimension k. And the first difficulty is, remember, at some stage we have 2 bundles we begin to work with. One was the restricted bundle, so the bundle of spinors on M are restricted to M. The other one was the bundle of the intrinsic spinors on M. But in that case, I told you in this case, it was very important to have this normal vector field. Because here you don't have any actual normal vector field. So how do you work with that? Well, the first thing is that I assume the ambient manifold M bar to be spin. And it's easy remark that M submanifold is spin exactly where the normal bundle, the spin bundle, is a spin vector bundle on M. So that's very easy. It goes even further.
That is, if you had given yourself a spin structure on M bar, the choice of the spin structure on M produces the spin structure on the normal constant of the person. So choosing a spinorial metric amounts to choosing a spinorial metric either here or there. So that's important. And then the key point is that what has to, so I'm going to assume, of course, that M is spin or normal bundle is spin. And so as a result, I can form the bundle of spinners on M. If it's not vector bundle, since it's a spin vector bundle, I can consider the bundle of spinners on M. And now, of course, the key formula, which replaces my isomorphism. Remember, I told you the bundle of intrinsic spinners on M and the bundle of spinners on M bar restricted to M. They're isomorphic, one copy or two copies, depending on the parity of the dimension. Here you basically have this identity there, or two copies again, depending on the parity of the dimension, the full dimension, and so on. So there is a discussion which is a bit more complicated here. And of course, the key remark, remember we needed an isomorphism for the Clifford multiplication, is the fact that if you start with a spinor field on this side, then the Clifford multiplication in M for the image, which I denote by twiddle on this side here, is the same as taking X, multiplying by the volume element in the normal bundle, and Clifford multiplication psi, and taking the image which lies here, taking the image there. And this makes sense because omega, of course, acts in the Clifford algebra on this component. So omega is a multiple of the volume form and NM, and in fact, I said a multiple because depending on, again, parity of the dimension or full dimension, you may have an I, you may have -1 for the full dimension, and so on. So I skipped up to a factor here, which is either I, either -1, or either both, you have this identity. And the key formulas at the spinor levels are the following one, which is very similar to what we have seen for submanifold theory before. Namely for the spinorial connection on the side, in the direction of X, you get the so-called ambient one. You get the same value of the tangential connection, and then you get this H trigo of X, Clifford group side. I have to warn you about what I've written here. Remember, H trigo, that's the second fundamental form in the case of a submanifold. So it's really, when I apply an X here to the trigo, this is now a linear map of the tangent bundle taking its values in the normal. And so now, when I write my Clifford group side, you see this linear map is going to act both on the two components of the psi. Psi, remember, is isomorphic to a component along M, the component in the normal bundle. So this notation here is a bit cryptic, but anyway, you can learn how to use it. And so now, of course, the key point is to have the so-called submanifold Dirac operator, which is the same as the usual intrinsic Dirac operator, and with the correction term, which is this H, which is the mean curvature vector. And again, you have to think of this H in the terms I told you. It's a function of M taking its values in the normal bundle, therefore the normal bundle acts on the component of psi, which is size M. So this defines the so-called submanifold Dirac operator. So I give you only one theorem to show you how one can play all the games I told you before, get estimates, lower estimates, upper estimates. I give you a low estimate, which has been obtained by Cadazi and Zhang and generalized by Morel just this year. So we take an embedding of a manifold M into M bar, so compact spin in the spin manifold. So now I need to make an assumption which was very similar to the positivity of something, so of course the assumption is more cumbersome. So the assumption is the following one. R denotes the scalar curvature of M as a Riemannian manifold. R curly R and underline. So of course the normal bundle as a connection, as I said, is the reason why this connection is going to be flat. So you have the curvature of the normal bundle. And then you make it an object which acts on spinners, like this formula here. So you get the normal spinorial curvature operator, Rn. And what I denote by lower, with the lower bar here, the lowest eigenvalue. So I'm adding up the spinor curvature to M, the lowest eigenvalue of the normal spinorial connection. And then I'm adding to this also the norm squared of this cube side, stress energy tension. So assume the sum of these three people is larger than the norm squared of the mean curvature vector, which is of course non-negative. Then So this side that I take is an eigenspinor, then automatically the eigenvalue gets this estimate, which is an interesting estimate in the sense that this, of course, brings automatically positivity, and of course this allows the curvature to be quote negative, which we never had before. So this is an example of a situation in which you actually get the lower bound for the eigenvalue of the Dirac operator in terms of various quantities, in particular in terms of this gradient that I mentioned, is the gradient of the eigenvalue. So the space of metrics can view this as kind of a priori estimate on a well-defined function, maybe the eigenvalue, in terms of its gradient square, which is a very useful identity which you can play with. And of course, in that case, you can discuss the equality case and you come up with a generalization of what's called killing spinners, which are solution of this, these identities, which are determined identities. One thing I have no time to talk about is speak about the fact that since Dirac is conformally covariant, there are a number of identities which are completely conform, which comes out completely naturally. You don't have to do anything, because if you discuss things properly, things are thematically conformant. So if you compare to submanifold theory, which is really a Riemannian theory, you can have in the spinorial context a number of conformal estimates which come up very naturally. That's why a number of people have considered the Wilmot function of submanifold using Dirac, because Dirac is naturally conformed. Okay, so I'm just giving you some concluding remarks. So in a sense, I can make this remark only now that I've spoken for 1 hour about the topic, which is the following one. Namely, when you start with working spinners, as a geometry, one thing which bothers you all the time is that really spinners don't have a well-defined dimension. They are really all over. They are all at the same time dimension 1, dimension 3, dimension 5. A given spinner is multi-dimensional. So in a sense, a priori, it's a nonsense to work to study submanifold theory, which means that you have objects of very well-defined dimension, and you study them with spinners. But in fact, as you know, sometimes it's still new things. It's just a paradox of which still gets into this basic shortcoming. In fact, it seems to me that something should be done, because I've been studying a given embedding, but I think if you start to work with foliation, you're going to end up, I think, to get interesting formulas, because you will have a family of submanifolds, and then you will have a family of Dirac operators, and I think we should be able to. Of course, for physicists, spinners being called part of the metric, and for them the very basic object is the gravitino, which is the particle of spin we have. So, in some sense, the gravitino generates the metric. And so, in some sense, the mathematicians should really start to be serious and look at not only spinners, but also spin object of spin we have. And in that case, the right operator is considered not the right operator, the line and trigger operator. And for the moment, basically, nothing is done there. So it seems to me there is still a lot of work to do, and not stop our consideration of spinners. To really take seriously this idea, it should be a spin geometry, but it should also work with the spin-up project. We believe that this corresponds to spin. And now the final comment, which brings me in a totally different direction in some sense, is there has been some work which has been done by Katharina Habermas, which I think has not been received enough attention. She attempted to do the following thing. Suppose you are needing Riemannian geometry, I want to do symplectic geometry. So in that case, so I told you that in this case, in the Euclidean situation, the group of the dwarfism is not simply connected, it's you need to go to double cover to get this simply connected cover. When you are working with a symplectic group, mostly it's worse, in the sense that the final group is not D2, it's D in that case. And so, in a sense, spinners would be objects corresponding to this universal cover. But you don't already going at the double cover, which is not universal cover, you already get objects which behave very much like spinners. Like many people have called the symplectic spinner. They are, of course, very important to the symplectic structures, which are very important for recognizing the number of formulas and for example in the Haskell theory. So Dirac operators that is attached to spinners, synclectic spinners, and it seems to me, particularly what she wants to consider is use some part of the theory of Gromov about pseudo-holomorphic curves and replacing the Cauchy-Riemann operator there by the Dirac operator. And well, she has the same number of results estimates. And it seems to me that this family of results have not attention to account since I was making a participant for spin geometry. That's a low range, possible range for spin geometry. So thank you very much. The way they have been operating was definitely proving proof ab absurdo. So they proved that if you assume this and this and this, then you get a contradiction. In the other case, it's a different thing. It's constructive because you actually build the psi and you show m is, the formula is m is the norm squared of something. And so connecting them is not so clear because finally what they prove is that the old objects they construct, they prove finally cannot exist. So of course, I mean, I completely understand what you're saying, but the logic of the two proofs seems to me that maybe there is something which will connect them, but it will not be through the two proofs. It is something different. I agree. So, see, one thing which has been misleading for some time, and I think Parker finally put really a final touch to this. I mean, I first, but some other people, of course, did believe that then, after all, if you can represent the mass as the energy of some particle, this particle should be important. But in fact, Parker showed very, very well that in fact there are many, many psi that you can take. There is no uniqueness at all in the way you can express m as the energy of some quantity. That is the norm squared, the derivative of some wave function. So after you have lost uniqueness, because you could think that this mass is represented by particle because it's the norm squared of its energy. But actually you can really show that you can make extremely many different definitions which lead to the same formula. So it's kind of a point. But maybe there is something still missing there. And, but no, certainly what you propose is a good program. But I don't think we should do that by taking the two proofs and merging them. Because I think they are, I mean, in principle, mathematically, they are really different in spirit. I don't think you can bring everything together because one is to construct an object, the other is to show that the object should exist doesn't exist. So it must be a different path.